Hey guys, today we're going to take a look at composite functions. Last class we looked at how to add, subtract, multiply, and divide functions. Today we're going to look at functions inside of other functions. Some terminology that you'll see is something that might look like this or like this. Okay, so that's pronounced of saying f of g of x, and these are equivalent statements to each other. And what it just means is that your g of x function has been substituted in to your f of x function, and it's just basically performing some sort of substitution. If we take a look at our very first example right here, and it says f of g of x, that's one way of being able to write it out. What we have is we have our f of x function, but wherever there's an x, it's no longer saying f of x. It now says f of g of x. And so that means that if our g of x is equal to 5x, then what we could say is we can replace that and say f of 5x. And what that means is when you write out your f of x function, wherever there's an x, we're now going to replace it with 5x. So we have 4 times 5x plus 1. We can then expand and simplify that, and we get something that would look like this, 20x plus 1. So the big thing that I would say is work from the inside out. And otherwise, it's a pretty straightforward process. So let's try finding g of f of x. So if our f of x is worth 4x plus 1, then wherever there's an f of x right here, instead of writing that, I could write 4x plus 1. So now as I expand my g of x function, I know that I no longer have g of x. My x has been replaced with a 4x plus 1. So I would have 5 times 4x plus 1. And then you can expand that, and you would get 20x plus 5, and that would be your simplified statement. Okay, those were in terms of x. Let's look at example 2, where we have something where we can get a numerical value now. So f of g of 2. So g of 2, we know that that means that from last class, g of 2 would mean that we would replace x's with 2's, and you get 5 times 2, which is going to give you 10. So this is like saying we have f of 10, and then in terms of that, when you write out your f of x function, wherever there's an x, you replace with a 10, and you'd be left with an answer of 41. So our previous examples, we've had f's and g's. This is saying we have f of 1. It's equivalent to writing something which you could say something like that, f of 1. And f of 1, just working from the inside out right here, if we substitute a 1 in for 4x plus 1, where there's an x, you replace that with a 1, you would get something that would say, well, I could do that up here. F of 1 would be equal to 5. And so then if that's the case, you now have f of 5. And so then that means that when I rewrite my f of x function, wherever there's an x, I can replace it with a 5. And I get a numerical answer of 21. Okay, moving on. Here we have a couple more examples. Here we have f of g of x. So know that writing it like that is acceptable. You could also write it like this, and they mean the exact same thing. And what that means is I have f of g of x. So my g of x statement says 2x plus 1. So I'm going to replace g of x and say it's just 2x plus 1. And so then when I expand this here, if I have x squared minus 3, I now have 2x plus 1 squared minus 3. And then from here, we want to expand and simplify that. So I can FOIL out my 2x squared plus 1. And if I write 2x plus 1 twice, and expand it out, I get 4x squared plus 4x plus 1. Subtract 3, and so I'd end up with 4x squared plus 4x minus 2. If you leave it like that, that's great. If you wanted to factor out a 2, that's fine, but otherwise I would just leave it like that. Okay, g of f of x. My f of x value is x squared minus 3, so I have g of x squared minus 3. I'm going to write out my g of x function, so 2 times x squared minus 3 plus 1. I can expand the 2 in here, and I get 2x squared minus 6 plus 1, which would equal 2x squared minus 5. Okay, so those first 3 examples, nothing too crazy. We could build up from that a little bit more. Okay, so example 4, the same type of example, the only addition now is they're going to say express the domain at the end. So if you have f of g of x, or g of x is equal to 2x, so I have f of 2x, which would be equal to the square root of 2x minus 1. And if I have a statement that says the square root of 2x minus 1 and they want to know the domain, well, I know that 2x minus 1 has to be greater than or equal to 0 because it's the radicand. And then I could add 1 to both sides. 2x is greater than or equal to 1. So x has to be greater than or equal to 1/2, and that would be my domain. For g of f of x, my f of x, well, let's actually rewrite this here. My f of x is root x minus 1. And so then for my g of x statement, I could say 2 root x minus 1. This part here, the radicand, x minus 1 has to be greater than or equal to 0. So my domain, x has to be greater than or equal to 1. Okay, we can look at these visually as well. So if you have a graph like we have on the right here, and we have an f of x function and a g of x function, if it says find g of f of negative 1, so remember that's the same as saying g of f of negative 1. I haven't talked about this yet, but don't get confused with thinking that this is something like saying g of negative 1 times f of negative 1. It's not a times value like you saw from last class. This is something in which you're substituting in. You have a composite function. So we work from the inside out, and we have f of negative 1. F of negative 1 is located right here, and that produces an output, a y value of 4. So it would be like saying what's g of 4? And g of 4, if I look at my g of x function and I go all the way up to 4, it happens to also be equal to 4. Kind of a weird first example. If you feel confident about this, I would pause the video right now and I'd work on examples B through D. Otherwise, continue to follow along a little bit. So g of f of negative 2. F of negative 2 is right here, and that produces an output of 5. So we have something here that would say g of 5, and g of 5, looking at my g of x function, would produce an output of 6. F of g of 1. G of 1, I'm just going to erase this to help out. Okay, g of 1 would be at negative 2. So I get f of negative 2, and f of negative 2 would be right here at 5. And then f of g of 2. G of 2 is right here at 0. And f of 0 is right here at 3. So hopefully those questions seemed reasonable. There's definitely a few questions in Michelson that's going to practice the same concept. Okay, so to continue on now, here we have something where we're now going to have functions with fractions over fractions. So if you have f of g of x, and you wanted to expand that, so our g of x is 1 over x plus 1. So it means when I rewrite my f of x function, wherever there's an x, here and here, I'm going to have to replace it with 1 over x plus 1. So we'd say 1 over x plus 1 all over 1 over x plus 1 minus 1. And then based off of that, they would want us to clean it up and then eventually state the domain from that. So can we turn that into a single fraction? We could write this over 1 right here, and you could times this by x plus 1. And what I would try to do is I would try to get your denominator just as a single fraction first, and then you could times by the reciprocal. So if you rewrite this here, you could have 1 over x plus 1 all over, this would say 1, and then this negative 1 gets expanded. So you'd have subtract x, subtract 1. And then if you join some like terms in this row here, you would have 1 subtract 1 would reduce with each other. And then you could clean that up. So we're left with something that right now says 1 over x plus 1, and it's going to be divided by negative x over x plus 1. So you know that when you divide fractions, you could multiply it by the reciprocal, which means that we could flip this denominator and you could times it by x plus 1 over negative x. And the x plus 1s would reduce, and you'd be left with something that would say 1 over negative x, or just negative 1 over x. So that would be your solution right there. And then they want us to be able to express the domain. So for the domain, it'd be very common to look at it and say, well, if I have negative 1 over x, I know that that means that x can't equal 0. And that's definitely true, but you also have to look at the process. And if at anywhere else there's a part in which you would be dividing by something that would produce a denominator of 0, you need to make sure that you also identify that in the domain. So looking at a bunch of spots here, you have these x plus 1s on the denominator. And so you know that if x was ever negative 1, it would also equal something that would be undefined. And so we would have the domain could be any real number, but it can't be 0 and it can't be negative 1. So what I would do right now is I would pause the video and I'd take the time to work on B. It's a pretty similar level question, but I know that there's a lot of details in these sorts of questions right here. Okay, so for g of f of x, we're going to have g of, and then we'll write x over x minus 1. And what we'll have then is we'll get something that's going to say 1 over, and then x plus 1, but we know that x has been replaced with x over x minus 1 plus 1. Just like the last question, we want to create a single fraction, and the best way to do that is to first work with our denominator to create that single fraction. Times this by x minus 1, times this by x minus 1. Then you could get something that would say 1 over x, and then plus x subtract 1, which would equal 1 over 2x minus 1 over x minus 1. And when you flip that, you're going to get x subtract 1 over 2x minus 1, and that would be your final answer. So in terms of looking at restrictions for this, you would see that your final answer has a denominator of 2x minus 1, which means that x could never equal a half. So part of your domain would say x can't equal 1/2. And then you would also know that if you have these x minus 1s here, you could also say x can't equal 1, and both of those would be identified as your domain. So anywhere along the process, make sure you identify that too. And I know that's one of those concepts that sometimes separates some of the top marks from each other. Okay, so many of you are going to take calculus, some next year, and actually most of you next year. And this next formula is part of the fundamental theorem of calculus. It's one of the first things that you're going to learn when you've finished limits and you're starting derivatives and you're trying to figure out what a derivative is. You're going to say, hey, I think I learned something about this during transformations and pre-calc. We're not going to look at the calculus component of it, but we are going to take a look at the idea of how this works in terms of being able to simplify some statements using composite functions. So the question is saying, given this formula of f of x plus h minus f of x over h, this very, very famous, well-known formula, what would happen when f of x is equal to 2x squared plus 3? And I know that the first few times when I did this back in high school and university, sometimes it was a little bit confusing. And I think the best thing to do is to break it up into a couple different parts. So what I'm going to suggest is let's split it into 3 parts: part 1, part 2, and part 3. And the denominator of h, we're just going to leave right there. And the back value of subtracting an f of x, well, we know in this case, f of x is equal to 2x squared plus 3. So we can just put that all in a bracket and make sure you include that in a bracket because that negative sign is going to have to be distributed through. And then aside from that, you have f of x plus h. And this is a part that really trips some people up. And so what it means is this: if f of x is equal to 2x squared plus 3, then what would f of x plus h be equal to? So it means that wherever I have an x, I'm going to replace it with an x plus h. So I'd have 2x plus h squared plus 3. So if that part was a little bit strange, just pause, rewind that. But all we're doing is we're saying that my f of x statement is now being replaced by an f of x plus h statement. So wherever I have an x, I'm going to replace with an x plus h, which is why instead of having 2x squared plus 3, I now have 2x plus h squared plus 3. So with all of this, now we want to expand and simplify it and see what we could do to put it in simplest terms. So this x plus h we need to FOIL out. So I'm just going to do that quickly and get x squared plus 2xh plus h squared plus 3. And then this negative gets distributed through, so it'd be minus 2x squared minus 3 all over h. Now this 2 here gets expanded in, and we could say we have 2x squared plus 4xh plus 2h squared plus 3 minus 2x squared minus 3. And then if you start to join some like terms on the top, let's see what happens. 2x squared, those go away. 3 and 3, those go away. And we're just left with now something that would say 4xh plus 2h squared over h. And so they all have an h in common, which means we could factor and reduce out an h. And so if you do that, you'd be left with 4x plus 2h as your final answer. And again, this is going to really help figure out how derivatives really start to work. But for our sake, this is all we're looking for. So I know in your homework, I think question number 10 has a bunch of these, and so you'll be able to practice a few more of them. But you'll rarely hear me say this, but it's one of those guarantees of questions you're going to see because of how important it is for your future. Okay, so couple final points to think about is let's see if you could work backwards. So for example 8, we're going to have something here that says for the function y equals 1 over x squared, determine possible functions of f and g of x to create something in the form of y equals f of g of x. So if we have something like that, what we want to do is we want to say this: what can we make f of x and what can we make g of x, so that our final answer is going to be 1 over x squared. And if you think about what you're doing is you're going to put your g of x into your f of x as a substitution, because the g of x is on the inside here. And so that g of x value, if we say that that g of x value is an x squared, and we say that my f of x value is taking the shape, the shell of a 1 over x, some sort of fraction right here, then you can actually do a quick check and you can make sure that as long as you check it and it works out, you know you've done something correct here. So if you say something like, well, what would we have if we had f of g of x? Well, my g of x is x squared. And so it's telling me that when I substitute in x squared into this form of 1 over x, I create 1 over x squared. And so I know I'll have done something correctly because I've got what the original question had asked for. So basically, the outer part, in this case the f of x, that's representing the shell. Like, what shape are you looking to replace something with, which is in this case some sort of fraction, some sort of I don't know if you want to call it a reciprocal function or something like that. And then the x squared is something that you can sub into that shell. I don't know what you want to call that, but we can call it the body or something like that. Anyways, that's sort of a safe way of being able to do it, but there's multiple ways of being able to come up with the correct answer. So just know that that's one correct answer. That's the most common correct answer, but there are multiple ways to be able to do that. Let's take a look at example 9. So for example 9, it's the same concept. We have f of x and we have g of x. And it's f of g of x. So again, f of x is going to represent our shell. G of x is what we're going to fill it in with. So what we could say is something like this. The shell, to me, for this question here, looks like we have something that would say x cubed minus 2, but filling in for that x cubed is a root x plus 1. And so again, let's see what that works out if we do a check and you do f of g of x. And if we're saying g of x is equal to root x plus 1, then when we substitute that into our shell or f of x function, wherever there's an x, we can replace with root x plus 1 cubed, subtract 2, and that checks out with what our original was. So we know we've done that correctly. So here's your homework for section 2.3. What I will say is question number 10 we can actually trim down. So question number 10, we'll just say let's do A, C. Let's do odds, A, C, E. E's a tough one, but for sure make sure you can do A and C. So if you do that, you should be pretty good for these questions besides that. So that's section 2.3. Thanks.